So before we start the lecture today, I'd like to review confidence interval, because you will see very soon that basically what we covered for the confidence interval is the roadmap for the remainder of this chapter, right? So, after we finish the lecture, I encourage you to go back and look at this slide, and you will see that we covered them one by one. But, now we are interested in hypothesis testing, not in confidence interval. So remember that for confidence interval, we considered calculating a confidence interval for the mean, right? So we wanted to see what's the range of the mean. And there were three total cases. Case one, which is the easiest case, we know the standard deviation of the population, right? Sigma is known. And that was using, so the solution for this was we convert things to Z, right? And Z always denotes standard normal distribution, right? So in this case, we deal with standard normal, right? So the second case, which is a little bit more complicated, is the case where we don't know sigma, so sigma is unknown. Instead, what we know is S, right? So instead of sigma, we know S, right? But the nice thing here is that we have many samples, right? So when we have many samples, the situation is exactly the same as before. Again, it's the standard Z distribution, standard normal distribution, sorry. So we convert, so here and here, we convert, our random variable into Z, which is standard normal distribution. So the exact same treatment here as before, right? And then the final case, which was the most complicated case, is where we don't know sigma, and we also have few samples, right? So n is less than 40, right? And this was the case where we said that, if we don't know the standard deviation of the population and we have few samples, we have to follow the student's t-distribution. Right? So that covers all possible cases for mu, right? And we considered one case for calculating a confidence interval for sigma squared, right? And for this, we saw that the distribution, so this is completely different. All of these distributions are, symmetric. So they all look, nice and symmetric. This one I didn't draw very well. But chi-square distribution looks quite different, right? So first of all, chi-square distribution never gets negative, so always starts from 0, and also is asymmetric, right? So in the final case, we have chi-squared. So a quick review of basically chapter 8. Now we can start, basically we can continue chapter 9. We have already started chapter 9. Okay, so in this chapter, what we are going to do, if I just go back, you remember, all of the analysis, all of our analysis on the, on hypothesis testing, we say that, this is, for example, 50, this is 48.5, and this is 51.5, right? And we basically said that, if our X bar happens to be here or here, we say that we reject the null hypothesis, right? So where does this interval come from? These actual intervals come from confidence interval, right? So like how big that is, that's usually a 95% confidence interval around the mean that we think is the mean, right? So that's where this, I got this question a few times that, where does this come from? So it's some percentage confidence interval, right? So in this case, the numbers are so round, it's like 48.5 and 51.5. So I'm sure it's not a 95% confidence interval. It's probably like 92% confidence interval or something like that, right? Okay. So when we want to do hypothesis testing on the mean, where we know the variance, right? So the variance of the population is known, right? And this is the first case in this table before, right? We know the variance of the population. So in this case, as with confidence interval, we follow the exact same procedure. We convert things to the standard normal distribution using this transformation, right? Which is for Z, right? So we say x bar minus mu divided by sigma divided by square root of n is a standard normal distribution. And then we do, test, we perform the test on Z. So exactly the same as confidence interval, we have one-sided hypothesis. So in this case, this is not about one-sided or two-sided. So after we create this, let me go back. So after we calculate Z, so this is our, mu 0, and we have converted this to the standard case, so the mu becomes 0, because if you remember here from the previous slide, we subtract mu 0. So our mu 0 essentially becomes 0. This becomes Z of alpha divided by 2, and this becomes Z of alpha divided by 2. So we basically say that if we are here or here, we reject H0, right? So this is always the procedure for, finding out whether H0 should be rejected, or if it's in the middle, if it's here, we don't say we accept, because we might suffer from type 2 error, right? We don't know whether H0 is correct or not. So in this case, we say fail to reject. Right? So we will do many examples today. So this is what I wrote in purple here. If it's in this middle range, we fail to reject. If it's in this border range, we say that we reject H0. Any questions? Okay. So let's look at one example. So air crew escape systems are powered by a solid propellant. The burning rate of this propellant is an important product characteristic. Specifications require that the mean burning rate must be 50, right? So we immediately see that mu 0, which is the null hypothesis, is basically not the null hypothesis is that mu is 50. Mu 0 is 50. The standard deviation is 2. Number of samples is 25. And we have a sample average burning rate of x bar is equal to 51.3, right? So immediately after we see that sigma is provided, we see that it's basically standard normal, right? Whenever we know sigma of the population, that means that we operate with Z. And always remember, Z means standard normal distribution, right? So the best case scenario, the easiest case. Any questions about the question? Okay. So basically, if you want to draw what's going on, we think that, or we hope that, the mean burning rate is 50. That's what the requirement wants, right? And we collect 25 samples and we get 51.3. Right? So we want to see whether, 51.3 is close to 50, right? Meaning that, it's an acceptable number. In other words, what we want to do is we want to see whether there is a high chance that we get X bars as large as 51.3 or as small as, on the other side. So 48.7. I subtracted 1.3 from 50. Okay. So in other words, what we want to do, we want to calculate the probability of, these events happening, the colored area. Right? Why don't I just look at this number itself? Why don't I say, oh, what's the probability of getting 51.3? Because, we are working with continuous random variables, right? In continuous random variables, probability of X bar being exactly 51.3, what is it? It's 0, exactly, because it's integral from, A to A. An integral from A to A is always 0, right? So that's why we look at the range, right? We say that, oh, we are interested in this area under the curve, right? This area plus this area. Okay, so the parameter of interest that we have to specify is mu. We have to state the null hypothesis, that the null hypothesis is mu is equal to 50. The alternative hypothesis, the question never said that it has to be less than something or more than something, right? So when the question doesn't say anything, it means that it's a symmetric, right? It's a two-sided. So it's mu0 is not equal to 50. That's the alternative hypothesis. Okay. So since we know sigma, it's an easy case. It follows the Z distribution, right? Standard normal. So we do the transformation. And this is using the central limit theorem, CLT. So we calculate Z0, and we get 3.25, right? So 3.25 is a very large number for a Z, right? Remember that we calculated Z of alpha divided by 2, right? Which was 0.025. And that was minus 1.96, right? And this is Z of 0.025, and that is 1.96, right? This is from the table, right? Because we have used this number a lot that, hopefully now you have memorized it, but you don't need to. 1.96 is for a 5% confidence interval, two-sided, right? So this number comes from the table, 1.96, right? So what does it mean that, Z of 0.025 is 1.96? It means that this area under the curve, together, they are 5%, right? The summation of these two, right? That's what it means. And now we got a Z that's much larger than basically our Z of alpha divided by 2. Right? Basically, the Z that we got, Z0, is somewhere here. Is 3.25. Right? And remember from the previous slide, we said that, if we are here or here, we reject the null hypothesis, and we are obviously here. So because of this, because Z0 is more than Z of alpha divided by 2, which is 1.96, and this is 3.2. Because of this, we reject H0, right? We are in the rejection zone, so we reject it. Yep.
Could you just re-explain how you got 1.96?
Yeah, sure. So 1.96 comes from table, the table of the phi, right? So if you look at the table for phi, not sure if I have it in this slide, and don't want to change my application to show you the PDF from the crib sheet for the standard normal distribution, right? The table that we have been using for the table for standard normal distribution, right? That table gives us values of the normal distribution. So this is the standard normal distribution, and this is 0. It gives us the area under the curve for different values, right? For example, if you look at phi of 0, what is phi of 0 in that table? Does anybody know?
0.5.
Exactly, 0.5. Because that's half of the curve, right? So from the safe curve, phi of minus 1.96 is 0.025. Right. So what does that mean? That means that if we are looking at the standard normal curve, if we are here, 1.96, 1 minus 1.96, and this is 0, this area under the curve is 0.025, right? And that means that if we are looking at, so if you look at the question, if I go back, the question doesn't tell us what confidence level it wants, right? So whenever the question doesn't tell us, it means that alpha is 0.05, right? That's the convention, right? Whenever type 1 error is not provided, it's 0.05, right? And that means alpha divided by 2 is 0.025, right? And because of that, z of alpha divided by 2 is 1.96. Yep.
Do we reject the null hypothesis if Z0 is exactly 1.96?
That's not Z0. That's not the null hypothesis. Null hypothesis is mu0 is 50. This is the null hypothesis, right? And yes, we reject it, right? And the reason for that is we say that this is 0, this is minus 1.96, and this is plus 1.96. We say that the probability of x bar being here or being here by chance is, so probability of Z0 being less than minus 1.96 or Z0 being more than 1.96 is, what's this probability? What's the probability that Z0, so whatever Z that we calculate, is either less than 1.96 or more than 1.96? And remember, Z0 is what we calculate from here, right? So Z0 is this equation. X bar minus mu0 divided by sigma divided by square root of n. Yep. So that's an excellent question. Don't read this part. I haven't explained that. That's why you haven't understood. Yeah. So there are two solutions for this question. Both of them are correct. I'm not using the solution given here. I'm using another solution. So the question was, where does this p-value come from, right? 0.001. And I will explain that, right? So we haven't, we are using a different solution. We are not using, this solution here. So if we go back to the question, oops. Did Did I lose?
No, it's one more back.
One more back? Yeah, there you go. Thank you. So any ideas what is this probability? So basically this Z bar means that you get some X bar, right? So this Z0 is some X bar that you get from your samples minus mu 0 divided by sigma divided by square root of n, right? So what's the probability that after you calculate Z bar, so ideally you want Z bars, Z zeros that are close to 0, right? It means that you're actually, if Z0 is close to 0, it means that your X bar was actually close to mu 0, and that's a good thing, right? They actually they corresponded to each other. But if your Z bar is large, meaning that it's either a very large negative number or a very large positive number, that means that your mu was not probability mu 0. Your mu was something else, right? So do we know what is this probability that Z0 is either less than minus 1.96 or more than 1.96?
So like 95%.
Exactly.
Isn't it 5%?
5%, sorry, not 95, right?
Oh, it's 95 that
It's 95 is here. 95% that is here. So when we say alpha is equal to 0.05, it means that this area plus this area is 0.05, right?
well, less than.
Exactly. So that means that this area is 0.05 or 5%, right? So probability that, when you calculate Z0, you happen to be this far from the mean is only 5%, which is a small probability, right? So since this is a small probability, we say that this cannot actually have happened by chance. 5% is a very low probability, and because of that, your mu is not your mu 0 that you think. And because of that, you reject the null hypothesis, right? So if I go back here to the next slide, here, I'm here in this zone, so I am 3.25, much more than 1.96. And remember that this area or this area is the rejection zone, right? So I say that I reject the null hypothesis. I'm done, right? So I say my Z0 is more than Z of alpha divided by 2, and therefore we reject H0 because we are in the rejection zone. Done, right? So if I go back, what's this? So I'm actually here. My Z0 is more than Z of alpha divided by 2. I'm here. And because of that, I reject H0. Any questions? Yep.
How did you find out 5%?
How did I find?
0.95.
Yeah, okay. So if I go forward. So the question says that, our sigma is this, our n is this, our mu is this, and our x bar is this, right? But it doesn't give us what is the type 1 error or alpha, right? The convention is that whenever alpha is not given, you have to assume it's 0.05. So here, because alpha is not given, we immediately say that alpha is 0.05. Any other questions? Okay. So now we can look at the second solution, right? So the first solution, if I recap it, we calculate Z0, and if Z0 is here or Z here, meaning that is more than Z of alpha divided by 2 or less than Z of minus Z of alpha divided by 2, we reject, right? I like the second solution more because the second solution gives us the p-value, right? Because here we just said, with a probability of less than 0.05% of type 1 error, we reject the null hypothesis, right? But we just said less than 5%. We don't know how less than 5%, right? The second solution is nicer here in step number 7, right? So what we do in step number 7 is that after we calculate Z, so the two solutions, share a lot, just the final step is different. Here we say that, okay, Z is 3.25. In the table, I go and look for, 3.25, right? And the number that I see is, if you look at the table, is half of this. So 2 times of that is 0.001, right? So if you look at the table, phi of 3.25, and actually minus 3.25 is 0.0006. Right? So what does that mean? That means that if this is minus 3.25, this area under the curve is this value. Right? So since a two-sided test, we multiply by 2, so 2 times this will be this number. Or in other words, I look at, being this far from the mean in this direction or in the other direction, right? I multiply by 2. So this number is very important, right? So in fact, in our work, in my own research, we often have to, report the p-value, right? So we just simply, we don't simply say, oh, we reject that null hypothesis. So we actually use this hypothesis testing a lot. The reason we test it is that we develop different methods to do the same thing, right? So let's say, somebody else developed some method to, do some task, right? So let's not get into what the task is because, it's irrelevant to this course. So we have method 1 that does this task, and we have developed a new method that does the same task, right? And we want to actually show that, it's not just that our method gives us better results. Our results are also statistically significant, right? So because of that, we report the p-value, right? We say that, with a p-value of 0.001, our method is actually better than the previous method. Our results are not just chance, right? They are actually real results, right? And it's a very common thing in many different fields. When you propose a new method, you have to show that statistically it's better than the previous method, and you have to calculate some p-value, right? And I like this solution more because it's more, you provide the p-value in addition to rejecting the null hypothesis, right? So we say that we reject the null hypothesis with a p-value of 0.001. Yep.
What does the p-value give us? If we write it, it's going to just say that it's 0.0006 in the area of the rejection?
Can you ask the question again?
Yeah, I'm just wondering what does the p-value give us? Like,
What does it mean, right?
yeah.
Yeah, okay. Yeah, that's a good question. Any answers to that? So what does the p-value mean?
It's not the type 1 error.
Exactly. P is the type probability of, P is the same thing as alpha, right? So that's the probability of type 1 error. What is the probability of type 1 error? The probability of type 1 error is that, the actual mean was actually 50, right? So mean was 50, right? But you got a mean of 51.3, I guess, yeah. So you got an X bar of 51.3 just by chance, right? So that means that, in other words, that means that the chance of getting an X bar of 51.3, if your mu is actually 50, is 1%, right? Or it's a very unlikely event to happen, right? If something is 1%, is it 1%? It's 0.1%, right? So it's extremely unlikely for something that has a chance of 0.01% to happen. Sorry, 0.1% to happen, right? So in other words, that means that, your actual mean was here, which is 0. You got a value of, so your actually Z was 3.25, so your Z was here. And this area under the curve plus this area under the curve is 0.1%, right? That means that the chance of getting X bars that are here or here is 0.1%, or a very, very low chance, right? since the chance is very, very low, we say that we reject it. We reject the null hypothesis. In other words, mu is not here. Mu was probably something around here. Right? So, you know, when the Higgs boson, for example, was discovered, if you followed the news, even on the BBC, I remember they provided the p-value, right? So they said that we have discovered this particle, right, with the p-value of this, right? Because everything in real life, almost everything, or probably almost everything interesting is statistical, right? We are never sure about something, right? So, you know, they discovered Higgs boson with a p-value of 0.001, right? Something like that, right? So it means that what they discovered was very, very unlikely to be just by chance. Any questions? Okay. So this is the approach 2. So this is what we did before, right? So we say that, okay, this is z of alpha divided by 2. So these two numbers are z of alpha divided by 2. The actual z that we got was 3.25, which is around here. So we are in the rejection zone. So we reject the null hypothesis. Any questions? So we basically, just to recap, we solved this question using two methods. The method that provides the p-value is the method that I prefer. Okay. So now let's talk, yeah.
So like the lower the p-value, like the better the test is.
Exactly. The lower the p-value, the better, right?
Yeah, it's confusing because you say that we reject it, so I don't know, my head like that means like it's wrong or something.
Yeah, so we basically, like, the final conclusion that we can say, like, after this step, after step 7, we can say that we reject H0 with p-value of 0.1%, right? And I agree with you, the way it's, you know, phrased is a little bit misleading. So the idea here is that the smaller the p-value, the stronger your rejection, right? So whenever we say we reject something, there's a probability that we rejected that by mistake, and that's type 1 error, right? So it means that type 1 error is only 0.1%. Very low chance that we rejected it by mistake, right? So for example, you know, somebody was COVID negative and we said, oh, that person is COVID negative. Probability of us have making a mistake by saying that person is COVID negative is 0.1%. Okay. So now let's talk about the type 2 error, right? So as I said before, type 2 error always in real life also is much more complicated to calculate because you should know what your actual mean is, or you have to assume, right? So this is your null hypothesis, right? You assume your mu was actually 0, and your alternative hypothesis is that mu is not mu 0, and you have a little bit of difference, which is delta, right? And based on your, you know, based on your null hypothesis, remember that we have this range, right? So if I go back to the previous slide, we call this, you know, fail to reject, and we call these areas reject, right? So basically what we want to calculate in the next slide, which is the type 2 error, is the following. Type 2 error is the probability of being here, but being here by mistake, right? So probability of being here by mistake. That's the type 2 error. Type 1 error is the probability of being here by mistake. Right? Either here or here. right? Both of them are errors, so both of them have by mistake at the end, right? Oops, sorry. Okay, so now what we want to compute is, oops, where did this thing come from? Okay, so now what we want to compute is, probability of being here by mistake, right? That's what we want to compute. So what is that? That is actually, so we want to calculate probability of being here. By mistake, right? And what is that? So we have assumed that H0 is incorrect and H1 is the correct one. So that means that our distribution follows this curve. And probability of being, in this region means area under this curve. So it's basically this area. So that's what we want to compute. So this figure is misleading because it just so happens that Z of alpha divided by 2 coincides with the part that these curves intersect, right? And that's not the case, These two curves do not need to intersect exactly at the same location. Or in other words, Z of alpha divided by 2 is not the place these two curves intersect, right? In fact, the point that these two curves intersect is a very uninteresting point, right? So like the correct drawing would be something like this. So this is your null hypothesis, right? So I draw it in red. It means that it's actually incorrect, right? So your null hypothesis is actually incorrect, and the other one is the correct one. So your basically H1 is the correct one. So this is the correct distribution. And let's say this is Z of alpha divided by 2. And this is minus Z of alpha divided by 2, right? So we want to calculate the probability of being here. So in other words, we are interested in this area under the curve up to here. Basically in this green area. That's what we want to compute. So the area is computed from the correct curve. So that's one very common mistake that, people compute the area using the incorrect curve, right? So here we are interested in type 2 error. It means that the null hypothesis is actually incorrect. It means that this is not your distribution. This is your distribution. Any questions? Okay, so, once we know the fundamentals, calculating this area under the curve is trivial, right? So what is this area under the curve? We have this curve, so it means that you have to try to ignore the red curve, right? So I will draw another curve that doesn't have the red curve, so just the blue curve. So this is delta square root of n divided by sigma. So we are interested in this point, which is Z of alpha divided by 2, and in this other point, which is minus Z of alpha divided by 2. Right? So the area that we are interested in, the green area, is this area here. And that area is this area, which is this term, minus this red area, which is this term. So this is the equation that's also provided in the crib sheet for calculating type 2 error. And one important point is that when you use this equation, remember that you have to set up the question such that delta is 0, right? In the question, that may not always be the case, right? In the question, this guy, the correct distribution might be, less than this other distribution, so it might be here, right? So that means that don't care about the sign of delta. Always put in, a positive delta when you use this equation. Because this equation is, the way it's written, it assumes that delta is positive. So if it's negative, just convert it to positive. Okay, so let's look at, don't worry if, this seemed very complicated. It's not, right? Once you do few examples, again, this entire chapter, in my opinion, is much, much easier than chapters 2 and 3. These are trivial, always follow, step 1, step 2, step 3, a few steps. So the question is, the null hypothesis is 50, and the true burning rate is 49, right? So we want to find beta or type 2 error for the two-sided case with this alpha and sigma of the population of 2, and n is equal to 25, right? So that means that, we have 25 samples. And we want to see what's the probability of type 2 error. Okay, so delta is 1 because this is 50 and the other one is 49, so the difference is 1. Z of alpha divided by 2. Again, I encourage you to memorize this, 1.96, but it's okay if you don't. You can always go and look at the table, right? Z of alpha divided by 2 is not 1.96. So we look at this equation at the bottom of the page, and we have everything to plug in, right? We have Z of alpha divided by 2, we have delta, we have n, which is 25, and we have sigma. Yep.
Can you just draw the two graphs for this example?
What's the question?
Can you draw the two graphs?
Sure, yeah. Yeah, we can draw them, yeah. But first, let's plug into this equation and see what happens. So if you look at this equation, we have everything, right? Yeah.
Sorry, you're answering another question.
No. So I always plot, the distributions because that's something that I really like, right? And I think you should do the same because you're not solving a question blinded. You actually know what you're doing, right? So you see the big picture. So I'm happy that you asked that question because I always do that.
Did you say it's at 49, so should be like 51?
You can do that actually. You can forget about the fact that it's 49, and you can assume that it's 51 and you can proceed, or you can assume it's 49 and proceed. It doesn't matter. I can do both. Let's do both of them. Yeah. Other question.
So I was wondering, in your previous slide, you were talking about how there was the updated true mean.
Yep.
But that true mean is when it's U0 plus the delta value right there.
Yeah, exactly.
But then if our true mean is 49,
Yeah.
how come our delta value is 1? Because
Yeah, so that actually, the delta value comes from the null hypothesis, right? So if I go forward, the null hypothesis states that, let's say, by law, we are required to have a mu of 50, right? And let's say that somehow from our computations or somehow we know that it appears that mu is actually 49, is not 50, right? And we want to calculate the probability of type 2 error, beta, that leads to failing to reject the null hypothesis, meaning that we think that, actually mean is 50, meaning that, we abide by the law, our mean is actually 50 as required. But we do that by mistake, right? We want to calculate that probability.
I'm mainly wondering because, so the equation is, so our u there is 49, and then it's that equal to our mu 0, 50 plus the delta value, which is 1. But if you plug everything in, that would give you 51 instead of 49.
Yeah. So that's the same question. Yeah. So if I go back, the confusion comes from the fact that delta is always assumed to be positive, right? So it was the same question that can we assume that actually mu is 51? Yeah, you can do that. It's okay. Yeah, and we will do that. We will see that the result doesn't change. If you assume mu, the actual mu is 51 or the actual mu is 49, it doesn't matter.
Thank you.
Yep. So, but first, before drawing, let's see how to use this equation. So we have everything. So we plug in the numbers, right? For the first term, for this guy, we get minus 0.5, and for the second term, we get minus 4, and the final beta that we get is around 0.3, right? So it means probability of type 2 error is a large probability. There's a 3% chance that we fail to reject the null hypothesis, meaning that there's a good chance that we think that mu is actually 50. Right? So now let's try to plot what's going on, right? So the correct mu is 49. So I can draw the incorrect one in a red color, 50. So this is your incorrect mu. And your correct one, let's see what color we used. So here we use blue. We can continue to use blue for the correct one. So the correct one is going to be something like this. So this is 49. This is 50. And this is Z of alpha divided by 2 calculated from this 50, right? So, I mean, this is, writing like this is not strictly correct. Basically, what we should do is Z means that it's already has been transformed to the standard case, meaning that this is 0 exactly. And this is Z of alpha divided by 2.
So if you don't shift the curve, then like, it doesn't really make sense, your equation, right?
What is it, sorry?
If you don't shift the blue curve, like it doesn't, like the equation, like the ranges don't make sense.
Yeah, no, you have to shift them. You basically you have to look at them in the standard case, which is this case at the bottom.
Yeah, no, but didn't you say the blue curve has to be on the right side?
Oh no, it's okay. We can still do this, right? So here, so I can. It will be a little bit, hairy, if the blue curve is at the left side. So, but we can do that.
Sir?
Yeah, let me finish this first, and then.
Sorry.
So basically, the area under the curve that we are interested in is this area under the blue curve. Why? Because we think the blue curve is the correct one, right? Because we said that for the true burning rate is 49. So this is area under the curve that we are interested in, and this is minus delta. What was the equation? Yeah, it's actually here. Square root of n divided by sigma. Right? So this is the area under the curve that we are interested in. The only difference compared to the previous slide is that here, this area under the curve that we are calculating is on the right side of this curve, as opposed to being on its left side. Otherwise, it's the same. Or if you don't like this, you can actually you can say that, oh, it's 49, but I like delta to be positive. So what I'm going to do is, again, my incorrect one is 50. And since delta is always positive, I'm going to move the other one to 51 instead of 49. So this is the correct one. And the area under the curve that I'm interested is this area. So I draw basically remember this area is fail to reject. it's 0. So the area would be this area under the blue curve. Yep.
In the question we were calculating, we ended up with a value of negative 4.46. But the table for Z values stops at 3.99.
Yeah.
What do you do in that situation?
That's a very good question. So any ideas? Basically the question is, if you look at the table, it gives you values from -4 to, I guess, +4 probably. What do we do if the Z that we are interested in is like -4.9? Before it's 0, exactly, right? So, even if you look at -4, you see a bunch of zeros before some 1 somewhere, right? It means that these probabilities are so small, we can assume that they are 0.
Okay.
Yeah.
Thank you.
Yeah, sure. And same on the other side. These guys are so close to 1 that they are actually 1, right? So if you want to calculate Z of some number here, that's actually 1, the probability. Any other questions? Okay. So the question was that, in the table, this is 0. And that's usually the case. That's one way for you to check that you haven't made a mistake. When you calculate type 2 error, the second term is usually so far from 0 that it should be 0. If it's not, you probably have made a mistake somewhere, right? So this guy is usually -4, -5, -6, right? So this guy is usually 0. Or in other words, when you calculate the type 2 error and you're looking at, this area under the curve, you can assume that this area under the curve is equal to this area under the curve all the way to infinity. Okay. So the probability that, we fail to reject the null hypothesis by mistake is 30%. Remember that power of a test was defined as 1 minus beta or 1 minus 0.3 or 70%, right? We want the power to be as close as possible to 100, right? So we see that the power is not very high. Okay. So what does that mean? That means that when your true mean is 49 and you're only collecting 25 samples, there's a 30% chance that you actually think that your mu was 50, which is a high chance, right? So I repeat that again. When your correct mu is 49, and you're only collecting 25 samples from that distribution with a mean of 49, there's a 30% chance that you think that your mu was actually 50, right? And that's a high chance, right? So what we actually do for type 2 error, usually the other way around. We want to calculate n such that we have a known power, right? So usually when you design, for example, your project, you can say that, I want to collect that many, samples such that my power is, 0.9. So 0.9 again is a common power that is used, right? So that means that how many samples do I need in order to have a power of 0.9, right? So basically what happened here is that we saw that with 25 samples, we have a power of 0.7. Do we need more than 25 samples to get a power of 0.9 or less samples? So if I draw, let me so with 25 samples, this area under the curve was 0.295, right? and this is for n equal to 25. Right? Now I'm saying that this n is not enough, right? I want, instead of a power of 0.7, I want a power of 0.9. Right? In other words, what I want is I want to decrease this area under the curve from 0.29 to 0.1, and that means that I want to increase my n such that my distribution becomes like this. So still my, true mean is 49. So now this area will be 0.1, right? So here I showed, visually how to do that. Mathematically, what we want to do is that we want basically this equation. This is equation for beta, right? So we say that this is equal to phi of z of beta, right? And so we say that this is equal to phi of z of beta, and this equation that you see at the bottom of the board is a very, very hard equation to solve. In fact, it's an impossible equation to solve, right? In closed form. So what we do is that often this term is 0, right? So here, this other term, sorry, it's blocked by this thing. So this other term is actually 0, right? So that means that, we assume that this other term is going to be 0 anyways, and I'm going to assume that, the first term is equal to phi of z of beta, or in other words, z of alpha divided by 2 minus delta square root of n divided by sigma is z of beta, right? And then from this equation, I calculate n. So n becomes, goes to the other side, so z of alpha divided by 2 minus z of beta times sigma divided by delta, and the whole thing, because it's square root here, the whole thing to the power of 2. Right? So don't worry if you didn't understand the derivation. The derivation is not a part of this course, but that's how we calculate n as a function of other things, right? And that's the next slide. So the equation that actually this is here plus. There's a small, so I think in my derivation it was minus, right? Yeah, okay, now I see where I made a mistake. So here, where I wrote this is because this guy has to be positive, z of beta, so I have to plug in negative here. So negative, and then it becomes positive. But anyways, the proof is not important. It's not a part of this course, right? But it's basically, essentially, the next equation, which is this equation, is the same equation that we saw before. It's just that we calculated for n. Instead of the previous equation was for beta is equal to something, this equation is n is equal to something. Right? And the reason we say almost equal to is that because I assume this other term is 0, right? This other term, or this other term here, I assume this guy is 0, which is a very good approximation, right? So you can forget about almost equal to. You can say it's, it is equal to. So this is for two-sided test. When we have one-sided test, the equation changes to this one. Again, both of these are in the crib sheet. So what is this equation for? We have beta and alpha, so we know we have, the problem statement, specifies what level of type 1 and type 2 errors we need. We know the standard deviation of the population, and we know delta. Based on that, we can calculate how many samples we actually need. What is n? Right? So let's look at an example. Design the test so that if the true mean burning rate differs from 50 by as much as 1, so that means that delta is 1, the test will detect this with probability of 0.9. So that's the question. So we want to design a test, meaning that we want to find out what is n, such that if the true mean differs from 50 by as much as 1, we can detect that with the power of 0.9. Right? So again, this question doesn't tell us what's the type 1 error that you want, right? Always, if it's not given, type 1 error is 0.05. Type 2 error is 1 point power, so 0.1. And then delta, the question is 1, so we want to differ by as much as 1. Actually, the question didn't tell us what sigma is, but it should, right? So this is part of a question. Sigma must be 2. And the question must tell us that sigma is 2, right? So we know that the sigma of the population is 2. Okay. So again, from the table, z of alpha divided by 2, which is 1.96. Z of beta, so this one, you know, I don't expect anybody to memorize this. So again, for this, we can look at the table. This is 0.1. And the Z value is minus 1.28, right? So Z of 0.1 is going to be 1.28. And this is where I made a mistake in my derivation. I didn't put the negative, right? So this is minus value. Z's are always positive, right? So we have Z of alpha divided by 2. We have Z of beta. Sigma was 2. This is known, and delta is 1. So we plug in to the equation, and we get 42 samples, right? So we see that 42 is more than 25 that we had before. Right? Before we had 25 samples, we saw that the power was 0.7. Now that we have 42, you know, we satisfy the power of 0.9. Any questions? Yep.
Doesn't this assume that we've already found a Z beta for a different n?
Can you say it again?
Okay, so when we calculate Z beta, it's unless it's given. Oh no, it's okay. So it's given the problem here. That's why. Because in the formula we're given for Z beta, we already have, like, there's an n in there, so we'd have to calculate it based
Here?
on. Yeah.
Oh, no, okay. Yeah, so,
Right, because when you told us how to calculate Z beta, you showed us that it was the equation
no, yeah, I see your point.
that had the
So,
square root of n. So if we had calculated based on a different n.
yeah. So, no, so we didn't, yeah, so I see your question. So, you know, we did not calculate Z of beta based on another n. Basically, what we say here is that we say that we want beta to be 0.1, right? So this is always how we solve these questions, right? We say that we want the probability of type 2 error to be 0.1. Based on that, I go look at the table, and I see that Z of beta from the table is minus 1.28, right? So that means that Z of 0.1 is 1.28. And for this, I didn't use anything. I basically started from scratch. I'm saying that, you know, what is, you know, so in the normal distribution, what is the value here such that this area under the curve is 0.1, right? And that means that, you know, this Z value is minus 1.28. This is 0, right? So from the table, we see that this is minus 1.28. And for the sake of this equation, both Z of alpha divided by 2 and Z of beta must be positive. So you basically get rid of the negative signs.
Okay, I understand now. So it comes from, we're given a beta value where we're able to then go to the table and say, okay, Z of beta is going to be this value, and we can move
Exactly, yeah. Any other questions? Okay. All right, so where is the approximation? The approximation comes from the fact that I assume that, you know, when we look at the area under the curve, you know, this area under the curve is equal to this other area under the curve, right? Meaning that this area is 0. That's where the approximation comes from, and that's a very good approximation. That area is actually 0. In fact, like if you look at these numbers, they don't even exist in the table, right? They are so far below 4, -4, that they are not listed in the table. Okay. So when we don't know the variance, but we have a large sample size, so let's read out. So a test procedure for the null hypothesis, assuming that the population is normally distributed and that sigma squared known is developed. In most practical situations, sigma squared will be unknown. Even we may not be able to assume that the population is normally distributed. Now, if either of these don't satisfy, for example, we don't know that the population is normally distributed, so we don't know this, or we don't know sigma squared, that's okay if we have more than 40 samples, right? Because in those cases, the central limit theorem kicks in, and no matter what is your distribution, you know, when you have more than 40 samples, your mean is going to follow the normal distribution, right? So again, we in these cases where n is more than or equal to 40, we use, you know, the z. We use the conversion to z, right? Which means that, you know, we do x bar minus mu divided by s divided by square root of n, where s is computed from the data, and we say that this is z if n is more than or equal to 40, right? Exactly the same as confidence interval. Nothing changes. Now, a special case where we don't know sigma squared and n is small, as you guess, involves the use of student's t-distribution. Exactly the same as confidence interval, right? And that means that the transformation now is going to be x bar minus mu 0 divided by s divided by standard square root of n is going to follow the t-distribution. Are there any questions? Okay, so let's do this one on Wednesday if there are no questions.